Okay, so last week we had started studying the work, and we had defined the work done by a force. This is the work done by a force. If the force is constant, we had defined it like the force times delta R. This is the work done by a constant force. And the reason why we defined it in this way was mainly so that if we calculated the change in the kinetic energy of the object, this was equal to the total work done on the object. So here, the kinetic energy, we had seen that it was 1 over 2 mv squared. Now this relation over here will be our basic relationship when we are studying the potential energy. And most of your questions about the potential energy, the answer will be right in this equation. And probably in the second hour we will be starting to discuss the potential energy, and all of our discussion will be based on this. Now, any questions on this one, how we calculate the work? This is just a definition. And there were some non-intuitive consequences of this definition, such as if you are just holding the book with your hand and carrying it horizontally, you are not doing any work on the book. If you are holding it in an elevator and the elevator is moving up, for an observer, for a reference frame which is fixed on the ground, you are doing work. But for an observer, for you, for a reference frame fixed in the elevator, you are not doing any work. So this concept of work depends on the reference frame. Furthermore, the measure of the work, at least in your everyday life, is not how much you get tired. So if you are holding this book like this, you get tired. This is a heavy book, so you get tired quite easily, quite fast. Nevertheless, you are not doing any work. Now, any questions on these? On the definition of the work, on how we calculate the work? Now, one nice thing about this definition of the work done by a constant force, you see, when we started our Newton's dynamics, one of our fundamental relationships was F is equal to mass times acceleration. So if we know the force, in that case we can determine the acceleration, and from the acceleration we can determine how the velocity changes. Now, the change of the velocity, there were two kinds of changes. One is the change in the magnitude, one is the change in the direction. But if you are not interested in the change in the direction, let's say, but you are only interested in the change in the speed, in that case it is the work that would allow us to calculate it directly. So you see here the kinetic energy depends only on the magnitude of the velocity, depends only on the speed. And the change in the speed is determined by the work done, the total work done on an object by all the other forces. Now we can define the work done for each one of the forces acting on an object. For example, if you take this example, let's say initially it is at rest, then it starts moving. Then the work done by the normal force that is exerted by my hand is 0. The work done by gravity, the work done by the friction force, it is positive, because initially it was here, there is 0 velocity. Then it started moving in that direction, that it had an acceleration, it had gained a velocity in that direction, which means it has an acceleration in that direction, but acceleration is created by the force. So the only force acting on this book which will cause it to accelerate in that direction is the friction force. So there's friction force in that direction, there is displacement in that direction. So the friction force does some positive work on this book. So there are all these three forces doing some work, 0 or non-zero work on this book. And the change in the kinetic energy of the book is determined by the total work done on the book. Okay, any questions? And then there was the last thing that we were discussing was the work done by a variable force. And suppose you take this object, you just carry it around, and you reach this point, and there's a force acting on the object. So it might be the force that your hand is exerting, the force that is the different friction forces at different parts, or whatever you can imagine. Let's just imagine there is a general force. At this point, it is in this direction. At this point, it might be in this direction. At this point, it might be in this direction. We don't know. It might be quite a general expression. Now, in this case, how do we calculate the force? Remember, this expression for the work done by the force is valid only if the force is constant. Now, here the force is definitely not constant, but nevertheless, there is a trick that we always use in physics. We just divide this very long path into very small segments. So let's say this is how the object moves. We divide it into very small segments. You just take an arbitrary segment. Let's say this is the displacement of the object in that segment. That's denoted by delta r. The force at that point, let's just call it F at the point r. So the work done in this very small segment would be nothing but Fr multiplied by delta r. This is the work done on the object at this very small segment. Now, if we want to calculate the total work done from the point 1 to the point 2, let's call this point 1, point 2, the total work done as the object goes from 1 to 2 would be nothing but the sum of all these very small works. Eventually, of course, we will take the limit that these segments are very small. So each one of these work done in each one of these segments will be almost zero, but there will be infinitely many of them, and this sum is nothing but what we call the integral. From 1 to 2. This is what's called the path integral. Line integral, sorry. We will not be evaluating many line integrals. You will learn the line integrals in more detail in your calculus courses, but just understand what it means. You have this path, you have to divide it into very small segments, and you have to express, for each one of those segments, express the force at that point, take the scalar product with this very small vector, displacement vector in that segment, take the limit as sum over all of them, and take the limit as each one of the length of these segments goes to zero. This is what this means. You are just summing over the contributions of various segments making your path. Now let's do an application of this one. Now we had already studied the force that the spring exerts. So we said that let's take a spring. This is the equilibrium length. If you want to stretch it, by equilibrium we mean that if you just leave it like this, nothing will change. This mass over here will just stay there. If you want to stretch it, you have to exert a force. This is the external force. This is the spring force. Let's call this distance d. If you write the spring force as, let's say, its magnitude in the x direction, this is the x direction. Of course, if you are at if d is positive, that is, you have stretched it by d, then the spring force will be in the negative direction. is proportional to minus t minus k times t. This is what we call the Hooke's law. So if d is negative, that is if you are compressing the spring, in that case d would be negative, negative times negative, you get a positive number, so the spring force, if this will be a positive number, so the force will be in the positive direction. So these are also what we had discussed on Thursday. So let's calculate the work done by this spring. Now we will assume that, okay, here we have our spring. This is our mass. So we will assume that we start from x is equal to x1 and move our spring up to x is equal to x2. So how much work has the spring done? Now let us suppose, just for simplicity, we just carry the mass from here straight to point x2. We just hold it, move it towards x2. We don't make fancy motion. I mean, we will study what happens if you take your mass, this is point x1, this is point x2. What will happen if you take your mass from this point, move it here, back and forth until you reach the point x2. Even you go further away than x2 and then come back. So we will study such complicated path in the next step. First, let's just assume this is x1, this is x2. We just hold this mass and pull it towards x2. That is what we will be assuming. And of course, there are many forces acting on the system. We are holding the mass, so there is a force that we are exerting. There might be friction force, but the thing we are interested in is the work done by the force of the spring only, not all the other forces, only of the spring. So that's what we will be interested in. So this is our trajectory. We start from here and we come to the other point. And as usual, we just first divide it into very small segments. Let's take, here we have a very small segment. This arrow is the displacement within that segment. Let's say that this is our x is equal to 0, this point. So when the mass is in equilibrium, it is right at this point. So the position of this segment, we can call it x. And this dr would be nothing but dx in the x direction, a very small displacement in the x direction. This is our vector. What is the force? Acting on my mass when I'm right at this segment. Minus k times x in which direction? Well, it is towards x equal to 0. It will be always towards x is equal to 0. So that is, well, this is our x is equal to 0. This is positive x. So it's in the minus x direction. So we already have this minus 1 over here. So this is the force acting on my mass. Well, of course, if you look at this segment, the segment has that some width. The value of x at this point and at the other point, they differ. But they differ by a very small amount, which we will ignore. And eventually we will take the limit that this difference goes to 0. And that is when we obtain the integral. So that's why I just pick up any point within that segment. So the work done in that segment You see, I'm just looking at the work done at that segment only. I'm not looking at the work, all of the work, only at that segment, where the force is almost constant. F dot dr. This is the definition of the work done. You see here, in this segment, we are studying a system of constant force, because within this segment, the force doesn't change. So this will be equal to minus kx times dx. Now, to calculate the total work done, we have to sum all of these dW's. The work done in each one of these segments, we have to sum over them. And in the limit that we take the segments very small, we have infinitely many of them, so that gives us our integral. Now, what are the limits? What is the initial value of x that we start with in our path? We start from x1, that is the lower limit of the integral. What is the last value of x? x2. And if we calculate this integral, we will get minus 1 over 2 kx squared x from x1 up to x2. So the work done will be just minus 1 over 2 kx2 squared plus 1 over 2 kx1 squared. This is the work done by a spring. And this is the reason, it's this integral why we have this 1 over 2 over here. No, I'm just calculating the work done as I move my mass from the point x1 to the point x2. None of them are 0. Questions?
Yeah. Okay. This force that we have is the force that the spring applies to the...
True.
And the motion of the mass is away from the point. Force, the spring is from that direction. Why is that direction that this force is having on the other? Why is there work that this force is having?
Why is?
The work that this force is having, because this force is not in the same direction.
Okay, so that means that, at least in this sketch, if x1 is closer to the equilibrium point than x2, the spring force is in this direction, the displacement is in the opposite direction, so the work done should be negative. So the spring does negative work. So let's see if that is satisfied. x2 is larger than x1. So this term has a larger magnitude than this one. So we are subtracting a large negative number from a smaller positive number. The sum is negative. So here we have a negative work done. Of course, this relation is valid even if this is just a sketch. This expression would be valid, let's say, if x1 is on the other side, or even if x2 is on the other side, or x1 is on the other side. Still, whatever the value of x1 and x2 are, this relation will still be valid.
What's the relation between this work and the work that we exert?
Well, it depends on the acceleration. How much force do we exert? So if you tell me that this mass moves from x1 to x2 at constant velocity.
So that we must be applying a force that's constantly increasing.
No, if it is moving at constant velocity, that means at every instant the total force acting on this one should be 0. So at every point, we have to be exerting a force which is minus this one. If the force that we exert is always minus this one, then the work done that we have done will be also minus this one. Well, of course, if there is acceleration, if this is accelerating, if its speed is changing, you see the total work done on this mass is the work done by the spring and the work we have done. So if the velocity is not changing, if the speed is constant, there is no change in the kinetic energy, but that means that the total work done should be 0. The sum of the work done by the spring plus by our hand. If the speed is changing, then the change in the kinetic energy should be equal to the total work done.
I think we choose the direction of x prime right part of it, and f spring is left.
True.
The equation for the f spring comes from, where does the minus comes from?
This one.
From
Well,
direction or the
you see, we already know, if this is the positive x direction, this is our positive x direction, this is the equilibrium point. So we just stretch the spring. So we know that the force should be in the negative x direction. The magnitude of the force, we know that it is proportional to how much we stretch it. It is proportional to there is a proportionality constant that is usually called the spring constant. So k times d is the magnitude. Furthermore, it is in the minus x direction. So this number over here should be minus. So that is why we put a minus sign. But of course, this relation is valid even if you compress it. Because if we compress it, what happens is this d becomes a negative number. Negative times negative becomes a plus, so the force will be in the plus x direction. If you compress the spring, it will just pushes us back.
Why do we make such analysis to get the work? Why didn't we calculate it as force multiplied by the distance between x1 and x2?
The problem is that definition of the work, you see, this definition of the work is valid only if the force is constant. As my mass is moving from point x1 and to x2, the force is constantly changing. It has different values at different points. So I cannot directly use this relationship. This is not true. This is only valid for a constant force. So I did this trick that I divided my path into very small segments. For each one of these very small segments, the force is almost constant. So I can use that the work is equal to force times the displacement for each one of these very small segments. And then I just sum all of them up. So this way I can calculate the work done by a variable force, a force that depends on the position. Well, if x2 is larger than x1, the work is negative.
Maybe x2.
Good. Sure. I mean, you might start the mass from this point and move it to this point closer to the equilibrium point, or you might just take one of these points over here. The x1 can be over here, x2 can be over there. x1 and x2 can have any value. Just for demonstration purposes, in this sketch, I chose x1 to be closer to the equilibrium point. But this is valid for any value of x1, x2, whether they are positive, negative, one is larger than the other one, or the other way around. Other questions? Now let's see what happens if, instead of just carrying this mass straight from x1 to x2, I prefer to go through a wilder route. Now let us assume that I start from x1. Should I go left or right? Let's go left. Then I go towards x2, then I make another turn. Suppose I take such a path. So what will be the work done by the spring? Well, in this case, I don't even need to divide my path into very small segments because I already know the result for a straight segment of some finite length. I can just take this path this weird path, and divide it into a straight path. So here is one path from here to here. Here is the other path. This is one of them. This is the other one, second one, third one, and the fourth one. So basically this is what I do. I start from this point, I go here. Then I start from that point, I go to this point. Then from that, the last point to the middle point, and back to x2. So I divided my path into 1, 2, 3, 4 different segments of finite length. Again, I can just sum, to obtain the total work done, I can just sum all these works together. So let me give the points some names. Let me call this point x3, this point x4. So the work done as I go from, and this is x5, as I go from x1 to x5. So what is this work? From x1 to x5. Let's say here I go from x1 to x2, it is minus 1 over 2k, the last point squared, plus 1 over 2k, the first point squared. It will be the same here. So minus 1 over 2 k x5 squared plus 1 over 2 k x1 squared. The last point squared plus the first point squared. Now let's calculate the work done as I go from x5 to x4. What is the work? No, that is 5. This is 5. This point. x5 squared. And then we start from x5 and x5 to x4. Then we start from x4 back to x3. So we are on this path now. We start from x4, we go up to x3.
Minus 1 over 2 k x3 square x3 square plus 1 over 2 k x4 square.
And finally, the work done as we go from x3 up to x2, this is minus 1 over 2 k x2 squared plus 1 over 2 k x3 squared. Well, the total work will be just the sum of all of them. But now we see. Here we have minus 1 over 2 k x5 squared. Here we have plus 1 over 2 k x5 squared. So they just cancel. This term and this term, they also cancel. This term, minus 1 over 2 k x3 squared plus 1 over 2 k x3 squared, they also cancel. So what we are left with is minus 1 over 2 k x2 squared plus 1 over 2 k x1 squared. You can imagine much more complicated path. But the work done by the spring I mean, this is an explicit demonstration that it doesn't depend on how we go from x1 to x2. In the first case, we just took a straight path from x1 to x2, and now we take a much more complicated path from x1 to x2. And in both cases, the total work done was always minus 1 over 2k x2 squared plus 1 over 2k x1 squared. This is the general property of the spring. You cannot say the same thing for, let's say, for the friction. Let's make an example. Suppose you have this mass. The coefficient of kinetic friction is mu k. And let's say of static friction is mu s. You take this mass, you move the distance L, and then back. What is the work done by friction? Okay, there was one answer, 0. You see, if it was a spring, then if x1 and x2 they are the same, the work done by the force of the spring would be 0. Now here we have, this is not the spring force. Is the force constant, by the way, before we start? No? Is it a constant force or a variable force? A variable force. This is the path. Well, this is the path. Mu k is constant, so you're saying it's a constant force. Somebody else? Is it a constant force or a variable force? A constant force. Variable force. Variable force. Variable. It's variable. The magnitude is constant, but the direction is changing. So it's not a constant force. You see, the force is a vector, so it has these two properties, the magnitude and the direction. If any one of them change, in that case, the force is changing. So as I'm moving the book, let's say from left to right, the friction force is in this direction. If I'm moving the other way around, the friction force is in the other direction. So it's not a constant force. So what is the friction force then? The work done by the friction. Let me just say, okay, the magnitude of the friction force is mu k mg when it is moving. So what is the work done?
2 times minus mu k mg.
Well, let's just calculate it. There are two different segments, two different values of the friction force. Let's say this point is A, this point is B. So we have the work done as we go from A to B, plus we have the work done as we go from B to A. In each one of these segments, the friction force is constant, because as I'm moving from here to here, the friction force is towards the left. It has this constant magnitude, its direction is constant, magnitude is constant. So as I go from A to B, the friction force is constant. If I go from B to A, the friction force is again constant. But the value of the friction force from A to B is different than the value of the friction force from B to A. So let's see. Let's make some definitions. Let us call this vector from A to B delta R. Let us say this is our direction X. Now the work that we have done from A to B will be the friction force times delta R. The displacement is just delta R. The magnitude of the friction force is mu k mg. The magnitude of delta R is just L. What is the angle between the two? From A to B, the object is moving in that direction. The friction force is in the other direction. This is delta R. This is the friction force. The angle between them is 180 degrees. So cosine of pi, which will be, this is equal to minus mu k mg times L. The work that the friction force does as we go from B to A would be F friction dot, well, this time as we go from B to A, you say A to B, this is delta R. So if we start from here, we go in that direction, that is the delta R vector. If we start here, we go in that direction, that is the minus delta R. Let me call this prime. This is also prime. Now this time the friction force as we go from B to A is minus the friction force that existed as we went from A to B. Minus F friction. Delta R is also, delta R prime is minus delta R. So the work that the friction force does as we go from B to A is in fact this minus minus, they cancel. It is the same as the work that the friction force does as we go from A to B. So although the displacements are in opposite directions, the force is also in opposite direction as we go from B to A. So the work done is the same. As we go from B to A, this is our displacement, this is our force. They have the same magnitudes. The angle is still 180 degrees.
This also proof work is not a vector.
Work is never a vector.
This is proof.
No, you don't need this one. Even the definition of the work. You see how we define the work. If you take the scalar product of two vectors, it's just a number. It can be positive, it can be negative, but that positive and negative doesn't mean it has a direction. Yes, any questions?
What should we understand when work is positive or negative?
Well, you can say that if work is positive, if the total work is positive, you can say that there's kinetic energy increase. So the object will start to move faster. If the work done by an object is positive, it means you are trying to help it accelerate. But of course, there might be other forces who might try to slow the object down. But the positive and negative is never meant to imply a direction. Okay, one lesson from these two examples is that there are some forces, like the friction force, in which the work done by the friction force on an object depends only on the initial and final point. Here we have already seen an example, the spring force. You can take your mass and move it whichever way you like. The work done by the spring force will only depend on the initial point and also on the final point. It will not depend on how you go from the initial point to the final point, like this one. There are this other kind of forces, like the friction force, in which how you go from one point to the other point depends on which path you take. For example, this mass could have stayed right at the point A. Initial and final point is at the A. So if it stayed there, in that case, there wouldn't be any work done by the friction force. Or we could start from that point A, move to the point B, and come back. This is just another path which has the same initial and final points, but the work done is completely different. The total work done would be minus mu k mgl plus minus mu k mgl minus twice mu k mgl. So the work done by a force, by such a force, depends on how you go from the initial point to the final point. So these two forces you have to keep in mind. Now, we will make use of this definition, what this means, what this distinction means in the next hour. But before closing this lecture, let's just define another concept that we call the power. Now, this concept of power, I'm sure you are all familiar with the power of a car. So what do you understand when somebody tells you that a car is very powerful? Horsepower, okay. That's something that comes to your mind. So would you prefer a car whose power is equal to 1 horsepower or whose power is equal to 100 horsepower? Why?
Because it's faster.
It's faster. That's one thing that comes to your mind. A powerful car would tend to go faster. So why? The rate of work done. So basically, when you are riding a car quite fast, you are doing work against friction, the air drag. That amount of work that you do against the air drag will determine how fast your car can go. But of course, it's not the total work done. It will be the work that you can do per unit time. That will determine the force that you exert against the wind. So the power we define as the work done per time. Now, of course, in the limit, let's say delta W by delta T, in the limit, this is the instantaneous power, delta T goes to 0. You can talk about the average power, the instantaneous power. This is the instantaneous power. Now, another way of expressing the same thing is if delta T goes to 0, then your displacement is almost 0. There's a very small displacement in that very small amount of time. But if the displacement is 0, the force that you exert will be more or less constant. So it's a constant force. So if it's a constant force, then the work done by that constant force is nothing but the force times your displacement. If you divide it by dt, this is nothing but f, that's the velocity. So if, for example, a car exerts a constant force, the power will be proportional to the velocity that you can reach, the maximum velocity. So in the car example, if you want to go at a very fast speed, you have to be exerting on the car, the engine should somehow create a force that would balance the air drag. Now, if you go faster, the air drag will be larger, so you have to exert a larger force. Plus, you want to go faster, so your speed will be large. So that's why your power should be large. Otherwise, the car cannot go fast.
Speed is much or velocity?
Well, speed is, for vectors, you cannot really talk about whether they are large or small. It's the magnitudes of the vectors that are large or small. Well, the same thing holds for, let's say, a car on an inclined plane. This is your car. And you want to go uphill by, let's say, by a speed v. What should be the power of the car so that you will be able to go uphill by the speed v? Ignore air drag. What should be the force that the friction is exerting on the car? What is the magnitude of that friction force? Okay, first of all, is it kinetic friction or static friction? It should be static friction. If it is static friction, you don't really know its magnitude. You cannot say that the static friction is equal to μs times the normal force. That is the maximum possible value.
trying to make the car go downwards, so the friction force should be bigger than that.
Well, you see, the car is not accelerating. Let's say it's moving at a constant speed v. You're not trying to accelerate uphill. You just want to go with a constant speed. So the net force acting on the car should be 0. There are two forces, the static friction force and the weight acting on the car, and also the normal force. So we have, this is the weight, this is the normal force. What is the direction of the friction force? Uphill. So let's just choose our axis. So these are 90 degrees. So this is, let's say, our x-axis. This is the y-axis. The normal force will have some magnitude in the y direction. The friction force, we don't know its magnitude, but some magnitude in the x direction. And the weight, let's say this angle over here is theta. So this is theta. The weight will be mg cosine theta in the minus y direction plus mg sine theta in the x direction. So the friction force, the total force, let's say the x component of the total force, will be mg sine theta. Oh, sorry, this is in the minus x direction. Minus mg sine theta plus the friction force. The acceleration in the x direction is 0. So we see that the friction force is equal to mg sine theta. So the power delivered to the car by the engine should be just mg sine theta times v. This is the power of the engine.
Now we know the static friction.
Yes. But it's not mu s times n. We have just calculated the static friction coefficient. True. Well, you see, the friction force is determined, whether it's a static or kinetic friction force is only determined by whether the surfaces creating the friction force are in motion or not. Again, okay, I will explain both of them. The friction force is caused by surfaces touching each other, trying to move relative to each other. And that is the only thing that determines whether it is static or kinetic, and that will be the only thing that will determine the direction of the friction force, not the general motion of the object. You are correct in the sense that the car is moving uphill. But if you consider the friction force, the surfaces creating the friction force, it is the wheels. So let's just imagine this is a wheel on this incline, and the wheel is rotating like this. So the wheel, the surface of the wheel is trying to move backwards. So that is why the friction force acting on the surface of the wheel should be in the forward direction. Now for every object, if you want to determine the direction of the friction force, you always have to consider the surfaces creating. You cannot look at the general behavior of the object and say the friction forces should be in this or in that direction. Always you have to look at the surfaces creating the friction force. Now, before you go for a break, I have a question for you. How many of you are driving cars? What is the engine, the volume of the engine? 1.6. 3. Well, you are paying a huge fuel bill. Okay, the others? 1.2. 1.4. 1. Now, this size of the engine mainly determines the power of the engine. So, a car with a 1.6 liters engine would be, in general, more powerful than a car with a 1.0 liter engine. Mainly, they will be burning. If you are using a 1.6 volt liter engine, you will be burning more fuel per unit time. Well, burning more fuel per unit time means there will be more energy available for the translational motion, and hence there will be more power for the engine. Agreed? For example, if you are driving a 1.0 liter car and if you want to go uphill, you see we had already calculated the power necessary if you want to go uphill is mg sine theta times v. If your engine cannot provide this power, in that case, it cannot go with this speed v. You have to slow down. I mean, unavoidably you will slow down. But there's a way out. If you are using a car with a smaller engine, what you do is you lower your gear. If you lower your gear, you can. What it means is if you lower the gear, the engine will make more rotations per minute. At every rotation, this volume of the engine mainly determines how much fuel you burn at every rotation. So if you lower your gear, the rotations per minute will increase, and even a car with a very small engine can go uphill at a more or less a constant speed. So what does that rotation per minute do so that the car can go with a larger velocity uphill? You'll probably already do that, right? Okay. Why?
Creates more power.
How?
The piston.
How does the rotations per minute increase the power?
The piston moves, creates work.
Okay.
When we have work.
So how is the rotations per minute enter into this game? In general, that's how the car works. The pistons move, they do some work on the axe, which transfer it to the wheels start rotating and do work, etc. But how does lowering the gear increase the power? How? If you want to use torque, we will have to define the torque first. Okay. Any other comments? You have experience with this car. How does it work? Why does it work? Why? I mean, if you can relate it with power, how does it create more power?
It burns more fuel.
It burns more fuel. You see, at every rotation, it burns a fixed amount of fuel, and that creates a given amount of work. If you burn more fuel per minute, you will be doing more work per minute. Well, work per minute is what we call the power. So if you lower the gear, you increase the rotations per minute. If you increase the rotations per minute, you will be burning more fuel per minute, and hence your car will have more power. And if it has more power, this is more or less constant. You can go higher at a larger speed, even if you have a car that has a small engine. For cars that have a larger engine like the 1.6, you don't have this problem. So already the power provided by the engine is strong enough to go most of the hills in Turkey at constant speed. Now, any questions before you go for a break?
Can you say that the friction force on the surface is towards the minus x direction?
No, the friction force acting on the car is always in the plus x direction.
No, not on the road.
On the road, true. There's always the action-reaction pairs, so the road exerts a friction force on the car in the plus x direction, and the car exerts a friction force on the road in the minus x direction. That's correct. Okay, see you after the break.